Hello, everyone. Welcome to part 4 of earthquakes. We've learned a lot already about earthquakes. Um, we've learned about the 3 types of faults: the strike slip, the reverse, and the normal fault, where earthquakes occur. We've learned that most of the deaths and destruction that is caused by earthquakes is not caused directly by the shaking of the ground. In other words, you don't get shook to death, nor do you fall into giant cracks that opened up in the ground. Cracks can open up, large fissures. Generally, people don't die by falling in them. All right. We learned that people die because of building collapses and fires that end up burning uncontrollably because water lines are broken and firefighters cannot refill their tankers. We've learned that earthquakes hit you in 3 sort of shifts. All right. You get the primary wave, the compression wave coming through, and that will feel like a push-pull. Shortly after that, the secondary waves roll through, and that's what gives you your side to side or your up and down shaking. After that, the surface waves finish everything off. They're the most destructive waves. They cause the largest ground movement. They cause the ground to roll. And they have the advantage of moving through after 2 sets of waves have already passed. So they can sort of finish off things that have been weakened. All right. We also talked about aftershocks, okay, as an effect, a major effect, a devastating effect of earthquakes. And we'll review that in a minute. Yesterday, though, we talked a lot about the moment magnitude scale, which is the scale that we use to measure earthquake intensity or magnitude. And remember, it's based on the total amount of energy released by an earthquake. It's more accurate than Richter. Remember, Richter's scale only used 1 data point, how fast the ground shakes at a seismic station, whereas moment magnitude uses the total amount of energy released by the earthquake, which includes how fast the ground shakes and how far it moves. Remember, the difference between a magnitude 5 and a magnitude 4 earthquake is not just 1 unit, all right? For every number you go up on the magnitude scale, it increases the energy by a factor of 32, okay? So a magnitude 5 earthquake is 32 times more powerful than a magnitude 4. A magnitude 8 earthquake is over 1,000,000 times more powerful than a magnitude 4. And this is why we've never recorded anything greater than a 9.5 on this planet. We've never hit a 10 or 11 or 12, even though the scales don't stop there, because it's just a massive, it's hard to wrap your head around that amount of energy being released. If you remember, yesterday, in yesterday's video, we took a look at the magnitude scale. I told you what I really like about this is it shows that inverse relationship. Over here, we've got magnitude. Here, we've got frequency. So you notice as magnitude increases, earthquake frequency decreases. And that's a good thing. I couldn't imagine living on a planet where we get over 1,000,000 9 to 10 magnitude. This planet would be a big pile of rubble, right? Okay, so I'm going to post this particular chart to our Schoology page so that you can reference it quickly. Maybe go back through the energy equivalents here. Look at some of these historic events that match up with it. Okay. We finished off yesterday talking about aftershocks as a dangerous product of earthquakes. Remember that your main 3 shifts of waves have already passed through. And then in these large magnitude events, like the 9.1 we had in Japan back in 2011, you can get thousands of aftershocks afterwards that will continue to do damage. Okay? Some places that have had large magnitude events, the ground seems to shake constantly for years after earthquakes. Okay? So aftershocks are a powerful force. And they have to be reckoned with. They have to be dealt with if you're staying in these earthquake-prone areas. All right. So fires, building collapses, aftershocks. Those are three of the most dangerous and deadly effects of earthquakes. But there's another one, and it's called liquefaction. All right. So, liquefaction is a process in which, sorry, I went too far. Let's go back one more. All right. So, liquefaction is a process in which the shaking of the ground causes soil to act like a liquid, almost like quicksand. It occurs in areas where the soil is full of sand, silt, and water. Let me give you an example. Seattle is a city that is built right on the edge of a bay called Elliott Bay. At some point, they decided that they wanted the city to extend a little bit further. So what they did was they brought in a lot of dirt, a lot of what we call fill. They dumped it into the lake and they built a seawall so that they could build on top of it and push the lake further over, essentially, or the bay, I'm sorry. Now, it's these areas where the soil is going to be sandy, it's going to have a lot of water mixed in, that are especially vulnerable to liquefaction. If you build a building or a bridge on this stuff, it's going to plunge during an earthquake. So I have a short video here. This comes from Christchurch, New Zealand. New Zealand gets a lot of earthquakes. And you're going to see a man who went out into his garden and shoveled some of this soil that had been liquefied and had now dried. He shoveled it back into his wheelbarrow, and he's going to take it across a cobblestone driveway. All right. Now, when he starts pushing the wheelbarrow, I want you to focus on the material at the bottom of the wheelbarrow here. Okay. So I'm going to sit back, play this video, and let's see how liquefaction happens.
So this is the liquefaction out the back. Dug it out, so you can see across the rose bed all this sand has just come up out of the ground, and I've got a wheelbarrow full of it at the moment. It looks quite solid. So you'll see this re-liquefy as we go back out to the driveway, particularly as we drive across the cobbles on the driveway.
Watch the soil on the bottom of the wheelbarrow, closest to the bottom of the screen.
Now, here. Now onto the cobbles. We're shaking now from liquefies. This is exactly what happens to the city. The building is on top. Just turns to liquid. Then we'll stop moving. Solidifies or stabilizes structurally. So this is why buildings are busy falling over with this liquefaction happening from solid to level liquid.
So this is why buildings are busy falling over. You get essentially dry soil that turns into a quicksand-like mixture. Okay? So you saw the material in that wheelbarrow. If you would have built anything over top of material like that, you would have lost it. Okay? That's one example of liquefaction. Now, liquefaction also was a problem in Japan in 2011. Okay? And I'm going to show you a short video here in an area that was built over Tokyo Bay. So another area where we had soil that has a high water content and it's quite sandy. So watch this one.
Okay, we have earthquake right now, and this is actually moving. You see the cracks moving? That crack was not there. This whole earth earth is moving, I felt like I was drunk. I could see different parts. I could, ooh, wow, there was water just coming up right there on the ground. And the ground is just swaying right now. I don't know if you can see this on video. The crack is getting bigger and smaller, going back and forth. And there is water coming up all over in the park right now. This crack is just moving. There's water. I don't know if water lines are broken, but this water was not there a minute ago. It's coming up different places. Here it's coming up through the sidewalk. The buildings were making a racket. I seriously thought I was sick first because I didn't know what was going on. I could just feel like I was disoriented, stepping over another crack. I wouldn't be surprised if the trains are not running anymore. I'm on my way to the train station. We've got a little lake, and here's a huge crack. And it's still moving. It's just going back and forth, swaying. It's making me kind of nervous. Especially since this is reclaimed land that I'm on right now. This used to be part of Tokyo Bay. And they created this land by throwing landfill and mountains, rocks out here. And so this land could just go potentially. I don't know.
All right. So amazing footage shot by a man in Japan there. And you can see how spooky these large magnitude earthquakes can make the landscape. Okay. The final thing that I want to get into as far as earthquake effects are tsunamis. Now, tsunamis are defined as a series of waves triggered by an earthquake, volcano, or landslide. I should say a landslide into the sea, right? So we've got a whole presentation and lesson on tsunamis. So we will come back to that later. And I think this is a good place to stop because I know this video is going to stimulate quite a bit of discussion in class. The images and the pictures that you've seen, you've probably never seen before. So I'm hoping that it stimulates some discussion, and we will have Earthquakes Part 5 very soon, where we'll talk about predicting earthquakes and how we measure ground movements prior to earthquakes, and how that might give us a clue that one is about to happen. Thanks for tuning in again, and we will see you in our next video.